This is step 2, 2013, question 8. I had a good time answering this question. Very fun. It looks like quite a tricky question if you just like read it at first glance, but it really is not too bad. And a fair amount of people did well on this apparently. So yeah, let's go over it. So we have a function f of x, which is greater than 0 for x greater than 0. And it's strictly decreasing. So a decreasing function essentially means that f dash of x, or the derivative of the function, is always less than 0 for its domain. And it wants us to show that for a different variable t greater than 0, where AOT, oh my god, that reminds me of the anime AOT, but yeah, AOT, A naught T maybe. And yeah, so A naught T is the largest area of a rectangle to the chord with sides parallel to the coordinate axis that can fit in the region bounded by the curve y equals f of x, the y-axis, and the line y equals f of t. Okay, this is quite a lot to take in, so your best bet is like drawing it out first of all. So we don't obviously have the curve, right? But we can draw like a general decreasing curve. Um, so a general decreasing curve would just be something like this, right? Just as long it just needs to follow the inequality. No, sorry, not follow the inequality. I mean, it just needs to follow the rule that as our x value increases, our y value or f of x value is going to decrease. And it wants us to show that an area with sides parallel to the coordinate axis that's bounded between the y-axis and the line y equals f of t. So y equals f of t is just some constant line. So let's just say y equals f of t is something like this, right? Let's say this is y equals f of t. Okay. And we want a rectangle that's bounded between some point f of x. Let's call this f of x, right? Uh, and this is f of t. This is f of t, right? So the rectangle bounded between this and the y-axis will actually just end up being this rectangle here. Okay, it will just be something like this, right? Because that's bounded between the y-axis, right, which is this, the line y equals f of t, and the line and some value of f of x, right? And it wants us to show that a naught can be written as this. So, okay, if we call this, instead of f of x, we call this x naught, right? Let me write that a bit better. If we call this f of x naught, right, we've got f of x naught, this here will be x naught, just obviously, and this here is t, but that actually is irrelevant. So we obviously know that the area of any rectangle is just base times height, and our base here is just going to be x naught, and our height here is just going to be f of x naught minus f of t, which is exactly what we need to show, right? But there's still one more part to do. We need to show that x naught satisfies this. Now, note it says the largest rectangle. So this is actually an optimization problem, and we essentially want to show that basically just want to take the derivative of this function of x and t and make it equal to 0. So if we take the derivative of this, we get it'll be it'll be x naught f dash x of 0 plus f of x naught minus f of t is equal to 0, and then f of x naught, f dash of x naught, sorry, plus f of x naught is equal to f of t, which is exactly what we need to show. So yeah, not too bad of a start of a question. It's just understanding that, first of all, the line y equals f of t is literally just a constant line, and it wants you to find a rectangle. So it literally, the way you draw the curve just doesn't matter. You're just drawing a rectangle which has a height of f of x naught minus f of t, and our width is x naught. It doesn't really matter where you place it. It could be here, right? It could be anywhere. Just literally, it really doesn't matter. Let me just go back. Wait, I can just delete this. Cool. Okay. So that's part 1 done. Not too bad. Now part two is also not too bad. It's actually quite chill. If we do part two now, I'm gonna delete the first part of the question just so we can like save space because I don't really want to go into the bottom of the page. Cool. Let's just note this down though, because it's always like with STEP, it's always good to like note down any information you've like acquired in the first part, even though it's already in the question. It's still worth doing. Okay. Cool. Now the function g is defined to be this integral here. Okay, and we want to show this. Okay, so if we know that g of t is equal to 1 over t times the integral from 0 to t of f of x dx, then t g of t is equal to the integral from 0 to t of f of x dx. Okay, now we can see we have like a t times g dash of t. So what we can just do is say the derivative of both sides and just see what happens when we do that. So we'll get g dash of t plus t, sorry, that would just be g of t plus t dash, sorry, g of t plus t g dash of t. I don't know how I messed that up, but yeah, whatever. Is equal to the derivative with respect to t of this integral from 0 to t of f of x dx. Now, okay, what we have on the right side is essentially what we call the fundamental theorem of calculus, that which pretty much states that this here will go to f of t. Okay, now obviously you don't know that this is called the fundamental theorem of calculus, but you don't need to even know the name of this because it's quite obvious. Like if we have, let's say our f of x was sine x, right, and we integrated sine x from 0 to t, we would get it would be minus cosine of t. Now, if we take the derivative of that with respect to t, we just get sine of t. So do you see how we just go from f of x to f of t? I think, yeah, like you don't need to know that this is called the fundamental theorem of calculus. Like it's just quite obvious to prove regardless. So essentially t and x are just dummy variables. You're just swapping the variable. So what we can just say is that this goes to f of t. So then we have g of t plus t g dash of t is equal to f of t, and then we just bring that to the other side and we get t g dash of t is equal to f of t minus g of t, which is what we need to show. So cool. Again, not too hard. Like I think genuinely, like the difficulty of this question is just rearranging and just kind of trying to understand what's happening. But now let's see the second part of that. We want to show that with a sketch that this inequality holds true. Okay, let's just go over here. Try the sketch. Cool. All right. Let's just draw the same sort of curve that we drew earlier, right? Something like that. Now, the integral from f of x. If we think about f of x and f of t, f of x is something like this, right? And f of t is just this line here. Okay. Then, and we know that if we're basically the area we're finding, then if this is f of x, call this f of x, and call this f of t, right? And if this was our rectangle here, then just clearly the integral we're finding, so this is a naught t, okay? But the integral we're finding is from obviously from 0 to t. So the integral would just end up being this rectangle plus this part here, right? So then clearly the integral from 0 to t f of x minus f of t dx is greater than a naught t. Just do the sketch, right? Because the integral is covering more than the rectangle. But yeah, cool. Not too hard. And now we need to deduce that this inequality holds true. Now, if we go here, what we can do is we can split this integral up, right? 0 to t of f of x minus the integral from 0 to t of f of t. Okay. Now f of t is just a straight line. So it's like a rectangle in itself. If we think of f of t, the integral of f of t is just this from 0 to t. So um, it's just a rectangle with the width of t and height of f of t. So we can actually just rewrite this as this. Okay, and we know that the integral from 0 to t of f of x is equal to t from here is equal to t times g of t. So we have t times g of t. Wait, t g of t minus t f of t is equal to is greater than a naught t. Okay, and we know that t g of t. We want to show this, right? So we can just take t common, g of t minus f of t is greater than a naught of t. But we also know that g of t minus f of t is equal to minus t g dash of t from here, right? So we can sub that in. So which goes to t times minus t g dash of t is greater than a naught of t, and therefore minus t squared g dash of t is greater than a naught of t. Sorry, that's a bit squished because of this thing. I'm gonna move this down. Hey, hold on 1 second. Yeah, I'm just gonna move this down so we have more space. Cool. Yeah. So that was just rearranging, right? It was just using the parts before to kind of get it into this form. And maybe the trick here was realizing that f of t is a constant line, and then it's just a rectangle. But yeah, pretty chill. And that's the whole of part 2 done. So I'm gonna get rid of this whole thing here. And if you need to just take a screenshot or just rewatch this part. But we can get rid of all of this. Cool. Now part 3 took me a bit of time just because I made so many algebraic errors when I was doing it. And I think it really helps you if you do this question in like a specific form. So it does get a bit tricky now. So our f of x is equal to the natural log of, sorry, not the natural log, 1 over 1 plus x, okay? Therefore, if we kind of go to the inequality we had earlier, g of t is equal to 1 over t times the integral from 0 to t of 1 over 1 plus x, which is just g of t is equal to 1 over t times the natural log of 1 plus t, okay? And g dash of t is, okay, well, we don't need to do that just yet. T g dash of t is equal to 1 over 1 plus t minus 1 over t natural log 1 plus t. And then we just multiply t to both sides minus t. So minus t squared g dash of t is equal to natural log 1 plus t minus t over 1 plus t. Now, whenever I see fractions in this sort of form right here, right, it's very easy to manipulate this into two fractions, and I always just like to do that because there's no harm in doing it. So I always like to manipulate this into something like this. Okay, because then I can split this into a 1 minus something, and I think this is just a habit. Like when you do a lot of these questions, you'll just see, like when you see like denominators that are very similar, or numerators and denominators that are similar, kind of, but like are factors of each other, kind of, you can like force it to be an integer minus something, minus a fraction. So what we can just do here is split this up even further into natural log 1 plus t minus 1 plus 1 over t plus 1. Cool. Because this just splits into this here, right? Cool. All right. Now let's move on to the left-hand side of this page to work on the a0 t inequality. Now we're given a function of t and we have an x0. So, we should probably try and find x0 in terms of t. And, good thing about STEP is that all the information they give you is never not useful. And that's because we're going to be using this thing right here. Because this gives us a direct expression of x0 in terms of t, and we just need to rearrange that. So x0, f dash of x0 will just be minus 1 over 1 plus x0 whole squared plus 1 over 1 plus x0 is equal to 1 over 1 plus t. Okay, now we just rearrange and do some stuff. We're going to get minus x0 over 1 plus x0 whole squared plus x0 over 1 plus x0 whole squared equals 1 over 1 plus t, and therefore 1 over 1 plus x0 whole squared is equal to 1 over 1 plus t. Now what we can just do, right, is we can take the reciprocal of both sides, and what we'll get is 1 plus x0 whole squared is equal to 1 plus t, and therefore x0 is equal to the square root of 1 plus t minus 1. Okay, so now we've got x0 in terms of t, we can literally rewrite a0 of t as a function of just t itself. So I'm going to delete this here, okay, or I'm going to move it kind of over here. Wait, yeah, I'm going to move it over here, okay, and then now I'm going to move on and try and write this as just t. So I'm going to move on to the left-hand side again. So a0 of t is equal to square root of 1 plus t minus 1 times 1 over the square root of 1 plus t minus 1 over t plus 1, or 1 plus t, okay, which is equal to the root of 1 plus t minus 1 over root 1 plus t minus 1 plus t minus 1 over 1 plus t. Now, again, remember what I said about trying to split the fractions into an integer and my plus or minus another fraction? We can just do that here, right? So we get 1 minus 1 over, oh gosh, my pen is just like, okay, that's fine. I don't know what is happening. Okay, cool. Minus 1 over root 1 plus t minus root 1 plus t minus 1. Okay, now what I'm going to do is over 1 plus t. Now what I'm going to do is take the minus signs common. So we get something like this, which is 1 minus 1 over root 1 plus t plus root 1 plus t minus 1. Okay, and once again we're going to split this fraction even further into 1 minus 1 over root 1 plus t plus 1 over, plus this 1 plus t minus 1 over 1 plus t. Okay, that's equal to a0 of t. Now what you're going to get is this, so 1 minus 2 over the root of 1 plus t plus 1 over 1 plus t is equal to a0 of t. Now what we want to do is set up our inequality, and remember we proved this inequality up here. So, and we have minus t squared g dash of t in terms of t, and we have a0 of t in terms of t. So we can just sub in the values to make our inequality, which will be the natural log of 1 plus t minus 1 plus 1 over t plus 1 is greater than a naught of t, which is here just this. It's 1 minus 2 over the square root of 1 plus 2 plus 1 over 1 plus t. Now, clearly these two are just going to cancel. We can bring the 1 to the other side, so we get the natural log of 1 plus t is greater than 2 minus 2 over the square root of 1 plus t. And therefore, we can just take 2 to the other side. We can take 2 common and divide both sides by 2, and we get a half natural log 1 plus t is greater than 1 minus 1 over the square root of 1 plus t, which goes to, because of log laws, we can bring the coefficient as an exponent inside the bracket. So we'll get which is exactly as we wanted. So yeah, that's part 3 done. That's literally just it. That's the whole question done. This can be quite a quick question if you can spot this quickly. This just took me a while, just because the part 3 I made so many errors, and this is why I think it's so crucial to write your fractions as like, if you can, write it as an integer and a fraction, as a combination, because if you don't, you're going to be left with a lot of messy fractions and surds that you need to like simplify, and it just gets really messy. So yeah, write your fractions in terms of these. It definitely helps. And yeah, I hope you enjoyed. That was the question done. I'm going to go over the examiner report now, just to see if just to see what the common errors were this question. So sorry if this looks really weird to read, but essentially most candidates either received a very low or high score, which makes sense because I think most of the difficulty of the question was just understanding what was going on. Although I do think part 3 is quite accessible, even if you haven't done part 1 or part 2, just by like using the parts before. But there was some attempts that confused the line y equals f of t with a transformation of the curve y equals f of x. Yeah, to be fair, it is quite. I think it's just realizing that t is just some constant, right? So you can just it's just a line. It's just a straight line essentially, right? And in the second part of the question, there was some difficulties with the differentiation of g of t, but those candidates who successfully completed this section did not, in general, have any difficulties. Okay, yeah. I mean, to be fair, this generally looked like it was a standard question, but yeah, I think the main difficulty was just understanding what was going on at the start and applying that. But yeah, I hope you enjoyed. That was the question done. If you want me to go over any other questions, just put it in the comments, and I'll do my best to go over them. I have to go over the induction question of 2015, so I'll probably be releasing that one after this or tomorrow. I also might be going over some step 3, but the issue with that is that step 3 is, well, it's not an issue, but I find step 2 to be harder than step 3, and I think there's a good argument for that. And I just much prefer going over the hard step 2 questions rather than step 3. I might give some step 3 mechanics a shot, or even some step 2 mechanics, because literally no one covers step 2 mechanics for good reason, because it's just so difficult. But I might do some step 2 mechanics. But yeah, I'm just gonna go over the questions I enjoy. But yeah, give me give out a comment or write a comment if you want me to go over a specific question. And that's it. Thank you. Bye bye.